Okay, good afternoon. My screen is visible. Anybody?
Yes, sir.
Yeah. We'll see that rest of the introduction portion, and then we'll move on to question it. Yesterday we noticed that general consideration of DC and AC transmission systems, and we observed there is a advantages, disadvantages, applications, and modern trends, corona effect, all these things. Just only the brief introduction, will not go in depth of that. And the second unit is a converter circuits. As you are aware that in a power electronics we know that there is a different types of converters, like bridge converters and midpoint converter, semi converter, full converters, and then based on the pulse number, based on the quadrant operation, all the things that we come across. But here we will use only in the bridge circuits, that too three phase controllers only. Preferably we can say that directly as a three phase full converter. But here we don't use any semi converter, all these things. Directly we'll use as a three phase full converter. In that, that to 6 pulse converter and 12 pulse converter. In general we will use only the 12 pulse converter, but explanation, analysis, all the things, for easy to understand, we'll go for 6 pulse converters. And same thing, another 6 pulse converter connected in a series. That is only the case of converters. And here, as you are aware that controller, suppose it is a 6 pulse converter and all, we will use 6 devices, 1 3 5, and then 4 6 2, and these are connected to, suppose, A phase, then B phase, then C phase. These are the, just I'm done. These are the walls, 1 3 5 4 6 2 1. But strictly speaking, this is not a one device. In general, in case of HVDC transmission, whatever I mentioned, 1 3 5 4 6 2, it is not a one device, it is a combination of the devices. So that's what, there is a different types of devices are there, means series and parallel operation we need to consider. In that case, how many devices are connected in series, how many are in parallel, that's what choice of converter, connection. There is a series and parallel combination of a commutation group. That is one group we call it as, let it be 1 1, then 1 2, then and so on. We'll move on to 1 R something, and similarly 2 1, 2 2, and so on. So then S1 up to and so on, let it be S1, S2, and so on. We'll get it as a SR. So this is the way we are to connect. In that, the representation is, suppose if it is a P is a pulse number, that is equal to, we can represent, that is equal to Q R, let it be small, or you can consider S. So this is the way we will represent, where you can see that S is the value group in series, R is the value group in the parallel, and then Q is the pulse number, that is a commutation group of Q walls. If we use that way, then total pulse P is equal to QRS. That means that many series and then parallel combination we have to use it. But finally we consider as a converter only. But one device is not sufficient to get it carry that current capability and voltage capability. That's why generally we'll merge the devices in the group of walls and form it as a one wall. That inside we consider as a many number of devices connected in series and parallel. There is a characteristic harmonics also will be there, choice of converter configuration for any pulse number. So let it be, I want to know what is the harmonic order will be there based on your pulse number. For that, there is a one small formula will be there, Anyhow will come later. At moment just remember order of the harmonic H. Suppose it is in the DC harmonics, we can represent that is equal to NP. This is the formula for order of the harmonic, where n is an integer, p is a pulse number. P, suppose if it is a 6 pulse converter, then what are the types of harmonics it will be injected in a DC side, and similarly in a AC side? We can easily identify using this formula. Suppose DC harmonic, we can see that NP 6 pulse converter, let consider, then n is equal to integer 1 2 3 and so on. Then what are the harmonics will be injected? 6, then n is equal to 2, there is a 12, and n is 3 18 and so on. So we will get it as a order of the harmonic for 6 pulse converter. Suppose if it is a 12 pulse converter, then we can easily identify, let it be 12, then 24 and so on. So then we can observe that if I am increasing the pulse number, what will happen? The harmonic order. So higher order harmonic only will be present, lower order harmonic is going to be suppressed. Then it is very negligible quantity in the higher order harmonic that can be eliminated easily by using, there is a smooth reactor or a inductor. So that the output is connected, the voltage waveform is passed through the inductor or a smooth reactor, then automatically that harmonics also going to be suppressed. This is for DC side. Suppose in the case of AC side, there is a HAC based on the pulse number. We can see that order of the harmonic NP plus or minus 1. This is the formula for harmonic order or characteristic harmonics. We can see that under ideal condition in generally, there again P is equal to number of pulses and N is the integer. Then if it is a 6 pulse converter, we can notice the order of the harmonic N is equal to 1 and P is equal to 6. Then what will happen? 6 minus 1, let it be as a 5, and then 6 plus 1, that is a 7 for N is equal to 1. For N is equal to 2, then what will happen? There is a 12. So 12 minus 1, then that is 11, 12 plus 1 13 and so on. So this is the order of the harmonic for AC side, and previously we observed DC side is NP and AC side will get it as a NP plus or minus. That is the easy way to identify what are the types of harmonics is going to be injected in the AC side as well as the DC side based on the pulse number. So now I already mentioned you, there is a only 6 pulse and then 12 pulse converter only will be used in the HVDC transmission, preferably 12 pulse converter, and the lower pulse converters won't be used. As you are aware that by increasing the pulse number, what will happen? So suppose 1 pulse converter, 2 pulse, 3 pulse and so on. By increasing the pulse number, automatically ripple quantity will be minimized, the output voltage will be increases, means you can able to drive your output side in the high loads. At least this is for transmission side, we can transmit the more power. So this is the reason we will preferably use as a 6 pulse and 12 pulse converters in the HVDC transmission. That's what that is the choice of converter configuration. For any pulse number, we can divide as a NP for the DC transmission and NP plus or minus 1 is the AC transmission. Like that, based on your P transformers winding will be, Q is equal to this many, R is equal to 1, or S is equal to 2, like that. We can able to segregate your configuration, let it be as a P is equal to QRS. With that notation, we can add number of devices are in series and number of devices are in the parallel configuration. And there is a 12 pulse converter also I mentioned, no? 2 6 pulse converter connected in series, it will form as a 12 pulse converter. And then a finite smoothing reactor also will be used after converter. Generally, converter output will be as a DC. Let it be AC is available and we'll use as a converter, that output will be DC. Directly the DC cannot be used for your application side or a transmission side. We have to pass that to the large inductor, that we can say that to minimize the minimum extent of ripple quantity, that will use as a smoothing reactor. That is in one of the unit will cover that what is the effect of smoothing reactor in that area. Another one is there is a voltage source converter will be used generally, that consisting of a number of devices. There is a 6 devices will be there. Therein preferably will use as IGBT for normal application. For high rating application and a transmission line application will use as a thyristor only. In case of IGBT, anti-parallel diode also we have to connect. And then for control strategy of that, we can use as a pulse width modulation, that is a sinusoidal pulse width modulation and all use. And modern trends, if we consider, there is a lot of microcontroller based firing pulses are used to control the your firing angle. And if we come to the analysis part, that is the mentioned here, there is analysis of a bridge converter. In that case, there is a converter we are using as a line commutated converters, LCC. We call it as a LCC, that is a line commutated converter. Throughout the subject of the controller, whether it is inverter side or in the rectifier station, we will use as a line commutated inverters. That is and voltage control, voltage source converters also, but that is preferably in the black diagram and all what we are using as a line commutated inverters. And the HVDC converter, there are multipulse converters also. We are multipulse in the sense that this is obviously 6 and 12 pulse converter we are using. And this why we are using as a LCC converter, preferably all the controllers rectifier station or inverter station, the supply will be considered as a source side is AC supply, that we make use to commutate the device. This is very sensitive parameter in the high power application, when the wall misfire may takes place, or the device has to be properly turned off. If because very high voltages we are transmitting across the wall, we observed in case of power electronics also, voltage across the device, the VT, VT1, VT2 and so on. There we notice that when the device is turned off, there is a reverse voltage applied across the device. It can capable to withstand that voltage, because in the very high voltages, if the valve is failed, automatically there is a lot of fluctuation in the voltage level. So that's the reason we are using as a line commutated converter. The device has to be turned off very smoothly, and that is the reason we'll preferably use as a line commutated inverter. In the analysis part, once if we come to that, in general in the power electronics case, only one question we notice, that effect of source inductance and all, but all other explanation part we will consider only without considering as a source effect. The sequence, I think you may be known that let consider for 6 pulse converter. There is a 1 3 5, this is upper side, and then lower side also we have 3 devices, then 4 6 2. These are the devices. And if any case you consider in the sequence of conduction, as you are aware that you can start based on your pulse number. Let it be suppose if it conduct 3, and then 4, then 4 5, then 5 6, then 6 1, then 1 2, then 2 3 and so on, then 3 4. So now we can see that or you can start with 6 1 1 2, anything. So this is the conduction of the devices. One must be upper group device and another must be as a lower group device. So what we observed is, in the case of power electronics case, any sequence you can start any of the device, A phase device or B phase device or anything. Or if you want, you can notice that start with 6 1, then 1 2, then 2 3 and so on. You will get it up to 6 pulses in the output. So now we consider this diagram. Suppose if 3, 4 is conducting, 3 is the upper group device, 4 is a lower group device. And after that, what will happen? 4, 5 is conducting, and then 6, 1, so and so on. So here, any of the instant, what we observed is immediately the changeover is going to be takes place. So, but actually, if you consider strictly speaking, there is a 1, 2, and then 2, 3. Let consider any this instant, and then 3, 4. Any one instant I will explain. Now, what is the different in this area? 1, 2 is conducting initially. Let us assume that upper is a valve 1, lower is a valve 2. So, according to our scenario 1, 3, 5, 4, 6, 2, 2 is a C phase, 1 is a phase. Your output will be as a, let it be as a AC is your output. And immediately after 60 degrees, there is a 2, 3 valve is going to conduct. What is meaning of in that is, one is going to be turn off after 60 degrees and 3 is going to turn on after 60 degrees. That means completely 1 going to be off and completely 3 going to be turn on. But according to our transmission line scenario, or in the due to the transmission line inductance and all these factor, there is a some mean between, there is a instant is going to be takes place. It won't be happen directly from 1 is turn off and 3 is going to be turn on. In middle, there is a one more interval is going to takes place. What is that interval is? Anyhow, both sides 2 is there, the 2 will be remains conducting. But here there is a 1 and 3 together will conduct some duration. What is meaning in that is, suppose you can see 1, 2 is conducting, the changeover taking place from upper group device is 1 is going to be turn off and 3 is going to turn on. In that case, both 1 and 3 together will fire. Then 1 and 3 is belongs to upper group device and 2 remains in the lower group device. Therefore, this shaded area, how many devices is going to conduct? So here you can see that 2 remains both sides. That means 2 will be continue to conduct, and 1, 2 as well as 3. All the 3 devices are going to conduct during this instant. And after this instant, what will happen? Some mu is a overlap. That second unit completely related to this scenario only. There is a overlap period and without overlap period. Now we can see that without overlap period interval is 1 and 2 will conduct. Only 2 devices will conduct. After that, 3 devices are conducting. 1, 2, 3 will conduct. Then what will happen? During this instant, 1, 2, 3, all the 3 devices are conducting. Your average voltage is going to be dropped down. Then we are to see graphically what is the effect of valve voltage. Valve 1 voltage, valve 2 voltage, like that. For all the valve voltage, we can able to notice by plotting the graphs that previous power electronics graphs are entirely different with this graph, because this overlap period is very sensitive. Based on the value of overlap angle, it is going to be fluctuate that voltage, and that will affect on the which side, whether it is the rectifier station side or inverter station side, or which wall it is going to be jump that voltage from one level to another level. All that scenario is going to be observed in this. So that means 2, 1, 2, 3, 3 walls are conducting here. After some mu, let it be the mu may be 10 degrees or 20 degrees or 40 degrees or 60 degrees, depends on all your scenario. Now consider after mu, what will happen? After mu means that 1 is going to be turn off completely and 3 is going to turn on completely. Then what will happen? 1 will be vanished. That means completely off. What is remaining? Only 2, 3 is going to be conduct. Again, after 2, 3 instant, let it be after 60 degrees. Between that means this will happen only within a 60 degrees of time. Earlier in the power electronics case, total 60 degrees 1 2 will conduct, next 60 degrees 2 3 will conduct, and then 3 4 like that. But within a 60 degrees of time, two sub-intervals will come into the picture. One interval is 2 valve conduction 1 and 2. Another interval is 3 valve conduction 1 2 3. So that means within a 60 degrees of time we have to consider the 2 valve conduction and then 3 valve conduction. We have to find that average individually and then we have to sum it. We'll get it as a total average of the controller, and we have to notice the observation of valve voltages and average output voltage, where that voltage is going to be jump and how much it will be jump due to this overlap, because this overlap will affect on more on the controller aspect. And there is a, suppose if mu is greater than 60 degrees, then there is a 3 valve conduction as well as 4 valve conduction, because overlap is more and more. Upper group devices overlap will be takes place, lower group device overlap also will be takes place. Therefore with 60 degrees of interval, there is a 3 valve, not a number 3, it is a 3 valves. It may be 1 2 3 and then 2 3 4 like that. 3 valve conduction or 4 and 4 valve conduction. So there is a 2 valve conduction here and then 3 valve conduction. That is for overlap period is less than 60 degree. Here overlap period is greater than 60 degree. You have to consider 3 valve conduction and 4 valve conduction like that. So that is the effect of things. Now that means with overlap consideration and without overlap consideration, we have to derive what is your average output voltage, all these things. So after that, what we have to do is we have to analyze your performance using the plots. So lot of plots we have to do it. You can see that using graph sheet also you can able to plot for your better understanding, because that is very useful analysis from that. Then LCC bridge characteristics, we have to see that rectification side and first mode, second mode, third mode. Let it be first mode means overlap period is less than 60, and second mode means exactly overlap period is 60 degrees, and third mode is 60 to 120 degrees like that. We'll consider a different overlap period, and all the cases we have to plot your graphs, and you have to notice what will happen over 4 and 5 valve conduction, and then 5 and 6 valve conduction or 6 valve conduction like that, with different scenarios will be there that we have to notice in this unit. And then equivalent circuit of characteristics, we can observe the rectifier characteristics and then inverter characteristics, all these things. Another one is a there is a control strategies. We can see that DC link control means we are writing as equivalent circuit of a HVDC transmission. Let it be in the after rectifier station there is a DC voltage, and then there is a transmission line resistance, means that equivalent resistance will consider, and then transmission rectifier station resistance and inverter station resistance, and some of the taps will be there, sending end side and receiving end side. Transformer, because there is a AC will be available, you have to use the transformer to step up. Then there is a bus bar, that will be as AC bus bar, and we are using as a rectifier station. Then the transmission line, then inverter station, again there is a DC bus bar, and you have to convert it into AC by using as a transformer. That is one thing we have to see. And there is a basic characteristics also you have to notice. The in this unit there is a converter control characteristics, that is in the third unit. These are all analysis and overlap period and without overlap, that will be in the second unit. In case of third unit, you can see that what are the limitations of manual control strategy. After that we'll go for as a automatic control strategies and all. So that limitations you have to use. And there is a control hierarchy also will be there, valve group control and firing angle control. In that different control strategies will be there. In general, broadly speaking, there is individual phase control, IPC we call it as a. Another one is a equidistance pulse control. So these are the two major control strategies we'll explain in this unit. There is a one is a IPC, that is a individual phase control. Another one is a equidistance pulse control, EPC. So that is IPC and EPC is going to explain in this unit in depth. That is a constant firing angle control, inverse cosine control. There is some drawback will be there in the IPC also, that is individual phase control strategy and all. We will explain that part in this unit, and then we'll move on to equidistance pulse control. Again, that will be the pulse frequency control. There is a small black diagrams will be there how to control in the both scenario, IPC as well as the EPC, and pulse frequency control and pulse period control like that, and pulse phase control. There is a different control strategies is going to be explained in this unit, and that is only the in the case of third unit. And then in go for the fourth unit case, we can see that there is a protection. This is the scenario. We can observe a lot of protection things we need to take care, because when the walls are operating, some cases walls may be failure, and then firing pulses may be absent, or and misfire maybe takes place. That is all the things is going to be discussed in this fourth unit. In AC system, you can see that faults in a DC. What will happen as in a AC system? The faults in a DC systems are caused by some of the factors. That is the malfunctioning of the equipment and control strategies. So if the operation is misconduction, that means malfunctioning of the equipment, whatever the substation equipment, and the failure of the insulation. How the insulation is going to be failure due to lightning effect, or maybe due to the pollution, all these things. Now if that things will happen, then faults will occur. So then we have to detect that fault, and has to be protect in the switching and control strategies. Then only the power system will be in the stable condition. Otherwise, if anything will happen, it is a fraction of microseconds of time, all the equipment will be collapsed. So that is the major reason in this protection unit. There is in general faults due to malfunctioning. We classified some of the things. That's what I mentioned there. There is a arc backs, or you can say that backfire in a mercury arc walls and all. Olden days they will use mercury arc walls, but nowadays anyhow they are using as a thyristor walls only. And arc through, that means fire through, and misfire, all current extension. So all these things will come under general consideration, that is faults due to malfunctioning. And then commutation failure in inverters. So what is meaning of commutation failure? The process of turn off the device, we call it as a commutation in general scenario. But if unable to turn off properly in the within a interval of time, then other device will give the firing pulses, and that also will come into the conduction. There is a overlap is going to takes place, that leads as a voltage drop in the output side. Some spikes will be obtained in the wall. So all this scenario is going to be takes place when the commutation failure is going to be happen. And short circuit in a converter station, sometimes there is a short circuit also going to be takes place in a converter. So these are the some of the faults will occur, and we have to protect that using our DC reactors and circuit breakers, protection against over voltage, harmonic filters. So all the things we will discuss in this unit, that is a fourth unit. So that's what I mentioned, no? The arc through fault likely to occur mainly in the inverter station. Generally it will happen in that, and misfire also will happen in during the misfire. There is a lot of voltage, DC voltage side, and then it will jump that voltage levels. The high spikes will be obtained if it will happen. Then short circuit in a bridge circuit also, that leads as a problem. All these things is going to be discussed. And then overcurrent protection in a pole. There is a one particular pole side. Here is a not as a controller aspect, actually it is completely as a transmission line system. When we are using as a protection against overcurrent, we have to consider there is a selectivity and sensitivity, reliability and backup. All these things we have to consider. That factors must be considered in the designing of a protection system. When you are protection against the overcurrents and all, we can observe in anyhow will come later that controller. So there is a OCP and VGP like that, over current protection, and then wall group protection, and pole differential protection, and circuit breakers. So all these many aspects we have to consider for the protection aspect. While you are considering of this protection, you have to take care of that selectivity, sensitivity, reliability, and then backup. All these things we have to consider at what instant we need to punch that, and how to minimize that current, all these things. And similar fashion, over voltage in a converter station also you have to discuss disturbances on the AC side, because once the AC side will disturb, then automatically controller output also going to be disturbed, because if input is constant, then according to your firing angle you will get it as a average output voltage. But what will happen, sometimes if input itself as a fluctuating, and accordingly you have to adjust as a controller such a way that your output must be maintained in the constant scenario. Or if you want to vary that, you can able to vary all, because if input is dropped down, obviously output is going to be dropped down, but we have to maintain constant, so controller has to be take care of that. So for that, over voltage in a converter station, that leads in the disturbance on the AC side. Due to that, it may happen switching over voltages and the temperature over voltage, like that different scenarios will be there. Disturbance on the DC side also sometimes that leads the problem. Over voltage caused by the internal converter disturbances, I mean inside wall effect, or if any failure of walls, surge arresters, all these things is going to be discussed in this unit, that is in the fourth unit. So protection against over voltage, protection against over current, all these things. And then the over voltage protection in a converter station also, because there is a two stations here. Each station, what are the components will be there, I will give the schematic diagram of that and the components, and briefly explain each component, what is the function of that, all these things. So that will come under there is a protection. And then last unit, we can see that there is a multi-terminal DC systems. In a multi-terminal DC system, that will be is a very important thing. Normally in a HVDC transmission system designed and operate as far as a point-to-point system with two terminal, that is a converter station. And multi-terminal DC means MTDC. So multi-terminal DC is a MTDC, has more than two converter stations. So preferably 3 to 8 is a maximum. We cannot use that is the maximum limitation of the HVDC transmission also, because it is very costly to install as a station, whether it is a rectifier station or a inverter station. We have to build that, and then potential application of MTDC system we have to discuss. There is a two scenarios here. When this thing is going to be happened, there is a one thing in all HVDC transmission, bulk power transmission from several remote generating stations to the several load centers. At that instant only we will use as a I already explained in the introduction class, I mean first introduction previous class, there is a large distance and bulk power transmission only we are using as a multi-terminal DC system. Here that I mean normal HVDC transmission system, in that case there is a bulk power transmission from several remote generator. So one generator, because not only one station, generating plants are in different areas. So all the plants we have to synchronize through this DC, because directly AC cannot be synchronized. We have to see lot of frequency as well as the voltage, all these things. But whereas in DC, you just use as a converter from AC to DC, and then you can connected to as a common grid. So that is a bulk power transmission from remote generating station to the several load centers. Load centers also is a different load center, we can dispatch it. There we can convert again as a rectifier inverter station to come back it into the AC supply side. And another one is asynchronous interconnection between the adjacent power systems. So what is that asynchronous interconnection? That's what the frequency mismatch also is going to be synchronized using this DC transmission. and the reinforcement of AC network is a heavily loaded condition. All these things is the types of MTDC. That's what I mentioned here, types of MTDC and comparison of series and parallel MTD, because there is a two types broadly, if I call it as a means MTDC systems, series system as well as the parallel system. The parallel MTDC can further divide into as a radial system and mesh system. So like that, series MTDC and then parallel MTDC systems, we have to comparison of all these things. That will come under unit number 5. That is a comparison of series and parallel MTDC system. Individually you have to explain series and parallel, then you have to compare that two systems, and we can close that unit. So these are the about all 5 units basic introduction portion, and all more or less, this is just general knowledge aspect, as well as the one analysis will be there majorly in the second unit, and then in the third unit there is a control strategy, and then fourth unit is a protection. So like that, total HVDC transmission we can easily understand what will happen and at what instant it will be used, what are the components will be used in HVDC transmission, what is the comparison between HVAC as well as the HVDC transmission, and advantages of this. And even though advantages, many things are there, but still some of the disadvantages also will be there. All these things we have to come across in this. This is the basic introduction. This is what just 6 pulse converter valve configuration and all. And this is the individual syllabus of each unit I mentioned here. What will happen in the first unit, what are the topics. I already broadly explained all the topics, what are the topics involved in this unit and what is the impact of that. I covered all the things in the first unit in the portion, and then second unit, then third unit control strategies, and then fourth unit protection, fifth unit is a multi-terminal DC. It is very simple unit only, fifth unit only series and parallel multi-terminal DC system and comparison of this. So it is a basic only they given, and these are the just given some screenshots of location and history of HVDC project, where the HVDC links are available in globally, and what is the power rating, all these things I mentioned here. You can see, just you can glance in that when lot of in India and New Zealand and then Australia, USA, many countries they already established, and even our Visakhapatnam also 500 megawatt HVDC transmission line is there, and like New Zealand 1240 megawatt. So like that, many areas they use. Just given as a screenshot of where that HVDC lines will be established, and you can see in this line. HVDC project implemented in India, including the longest bipolar HVDC transmission. There is a, I mentioned in the introduction first unit case, what I mentioned is there is a 3 types of links. That is a monopolar and then homopolar, bipolar, all the 3 things will be there, and different areas they may be installed in the different thing. They have their own advantages and disadvantages aspect. But there is in the HVDC transmission from Orissa to Kolar, there is a Bangalore. In between there is a one HVDC transmission is there. That is the line picture of this. And this is the projects around the world. They installed in 6 megawatt, even 1945 itself, but that is not in the working condition. They didn't start that. They installed and they left. And similarly, many countries they installed in the different years. 1951 there is a Russia 100-kilometer line. Preferably it will be advantage only very long distances only, but that too high powers. In 1954 there is a Sweden, and 61 UK, and so on. You can see that again 64 there is a Sweden. So many countries, Japan in 65. So they have their some remarks also will be there. This is only just for understanding. That is not related to our syllabus aspect, but to know where the HVDC lines are existing, what is the voltage levels. So you can see that 200 kV if we are increasing the voltage level, automatically conductor size will be minimized. You can save the copper, all these things. But preferably some areas they will use only the one conductor, some area they will use two conductors. That depends. If you want to pass that through submarines and all, so all depends on that area, all these things they will consider. And these are the some of the HVDC links are available. And this one is a another thing is there is a thyristor after implementation of the thyristor because you can see in the previous one 1945, 51, 54 and all they don't use the wall, that is a thyristor wall. Now at that moment they use it as mercury arc rectifiers. So whatever function is using that, thyristor, same thing they make use of your mercury arc rectifiers, but that is very inefficient when compared to this. After technology is improved, they make use of in after some time they use it as a thyristors. From first power on you can even 72, 77 and all they use it as a thyristor. And these are the some of the projects different countries in different areas with different voltage levels and power rating. Even you can see here there is a China in 2010 5000 megawatt of power is a very huge amount of power they installed. And even 6400 megawatt 800 kV. And the distance also you can see that in China 2071 kilometers, so where it is economical after 500 kilometers, that's what in general. But how far if we are increasing that distance, automatically our saving also going to be increased proportionately, because once the distance is very high, if you want to transmit in the AC side, lot of problems will be there. That's why generally they will use as a DC transmission. So these are the latest updates. Still after this also may have, we have to check it that these are the things of AC transmission, I mean DC transmission. Then later they used as IGBT, also some cases they used because all semiconductor device technologies are improved a lot and more. So and then commutation aspect and firing pulse generation aspect, many cases this technology improvement will leads the advantage in the DC transmission and all. And these some of the in India we can see that these are the started in 89 and then up to 2012 there is a Agra, one of the line is there 1875 kilometers plus or minus 800 kV and 6000 megawatt power they transmitted. And still it is from 2009 onwards it is under construction, maybe now it may be completed, you have to check it. So and these are the some of the HVDC lines are available in India also. So these things we can see. And this is the actual black diagram of a HVDC transmission system. So once if you understand scenario, it is easy to see that black diagram. Always utility side means generating station side and then load side will use only the AC. But now you can able to convert, many applications are using as a DC effectively without after a few of years. I don't think so the AC applications will come in the things, because many electronic goods are using directly DC. If the DC transmission is also there in the distribution side, generally they will use this type of DC alone. But as of now we can see that generating stations are AC, then you have to convert it into DC form. This is the AC bus bar you are using as a rectifier station, this one, or a converter station. Converter station may be rectifier station or inverter station, depends on your firing angle. So that's what bidirectional power flow is possible here. Either you can transmit power from sending end to the receiving end side or receiving end to the sending end side, depends upon which controller will act as a what mode of operation. Now this one way you can observe here, straight away we can start from this side. This is the one direction, AC is available, that is what generating station, and we are using as a transformer here to step up that voltage, and then rectifier unit, that means total combined setup we call it as a one conversion station, and then we are using as a overhead lines. Some cases underground cable also possible based on the distance and all. Preferably we will use a very long distance, we can go with the overhead lines. And this, after that there is inverter station, you have to convert back to the DC to the AC, and again we are using as a HVDC transformers, and we will come back to that of the AC terminals, and we are using as this. So this is what a simple block diagram, or reversely also is possible. If any power is available in this side, you make use of this is AC input, and then you are stepping down up the voltage based on the tappings and all, and this controller, whatever both controllers are exactly same, only thing is based on your alpha. If you can use this alpha value related by as a less than 90°, then what will happen, there is a rectifier station here, and it will transmit like this the otherwise version, and you can make use of alpha is greater than 90°, then it will act as an inverter station, and it will back to the load side. Now it will become as a another side. So there is a bidirection power flow is possible using that. That's what I given here. These side, it may be solar or wind or whatever, you have to finally get it into that of a transmission line side, and AC to DC converter, and then these are the towers in HVDC transmission, and after the DC to AC converter station, these are the two stations are important. One is a rectifier station, another one is a inverter station. After that in the distribution side also we can send. So AC transmission lines are there, and we can distribute to the distribution side, and then further you can step down the voltage to the houses and business side, all these things. So these are the single line diagram of all these controller. We'll move on to next, we'll directly start with first unit in the next class. Then you can post your attendance and can leave. 25 are there.